finding two numbers with a sum of 30. We need to designate a couple of variables for those numbers. If I designate, say, x and y, I know that x plus y would equal 30. Now, apparently with these two numbers, if we put them together as a product, the product's going to be as great as possible. So as we get into this further, I'll explain what that means, but we're looking for the greatest product possible between these two numbers that add up to 30. We basically want to take that x and that y that represent the numbers and multiply them together. If we multiply them together, that forms the product. So let me do this. Let me build a function over here. Since we're talking about a product, I'll let my function be p of x. P of x equals product of the two numbers, x times y. Now there's a tiny problem here with the function the way I set it up. Since it's p of x, I'd like everything in terms of x, not everything in terms of two variables. So what I can do with this equation that I set up, this x plus y equals 30, if I solve that for y, just swing that x over, I can take what y equals here, and I can insert it in for y over here. That way, p of x, this function that stands for this product, is going to equal x times y, which is 30 minus x. If I distribute that x through, not only do I have everything in terms of x now, but I've got a quadratic. So part of the goal here is being able to set up some function that is a quadratic. From here, we're trying to find these two numbers based on that function we've set up. So what we could do is we could take this form that I have, this general form for a quadratic function, and I could turn that into a vertex form. If I turn that into a vertex form, what I'm going to know about this parabola if I graphed it out, I mean, think about this for a minute. The x squared term, the quadratic term. Notice the coefficient on it. It's -1. What we know about that parabola, it's opening downward, right? So the vertex would have to be at the highest point on this graph. If it's at the highest point on this graph, then those values that make up the vertex must be significant as far as relating to this question, what's the greatest product possible, right? That would give us those biggest values that we need. So let's go back and revisit how to turn this into a vertex form. If I'm going to turn it into a vertex form, one way we've done this is we've grouped our x's, and I'm going to rewrite this just a little bit, -x squared plus 30x. If I group my x's, we used a little technique where we completed the square to get to the vertex form. So how we did that, we had to make sure that we had a coefficient of 1 right here. If we didn't, we factored out whatever was keeping us from having that coefficient of 1. So I take the negative out. I have x squared minus 30x left. And then if you recall, we added on a little space. As we completed the square, we took half of the value in front of x, so -15. We squared that, so that's going to be 225. We add that on. And then we did have to make another adjustment. Kind of running out of room here. But remember how we took this value in front here, multiplied to this value here? When we multiply those together, we get -225. So the opposite would be add on 225. We add that on to the outside. So if I condense this down to where I now have the vertex form I'm looking for, well, let's see. This part, that condenses down to a perfect square. Still got your negative in front, right? And the rule was lead term is x. Next term is half of the coefficient on x up here, so -15. And then you got this plus 25, or sorry, 225 that's on the outside. There's my vertex form. Now that doesn't answer my question. My question is find these two numbers. So in finding the two numbers, what you want to do, if you establish what your vertex is, Vertex off of this would be 15 and 225. So what that means to us, it means that if this x-coordinate is 15, I let x and y represent my two numbers in the first place, then one of those two numbers must be 15. 225 is connected to the function. The function represents the product of these two numbers. So when these two numbers are multiplied together, we get 225 back, and that's the greatest value this function can have. So the only question left is, what's the other number? What's y? Well, it's 15 also, because if we know this is 15, plug in here, 30 minus 15, also 15. There's your two numbers. All right, so we've got this pen that's going to be built along a wall from 90 meters of fencing. We've got to determine the value of x that maximizes the area that will be enclosed. What's interesting about this problem is it doesn't specify the shape of the pen, but I'm going to assume it's rectangular. That just seems to make the most sense. Okay, so we're going to have three sides here for our rectangle, aren't we? Well, here, we're going to assume it's rectangular. So we're going to roll with the rectangular part. So here's this, we'll say our building. We're building our pen off to the side here. We throw some variables on there. Oh, I don't know, x and y always seems to make the most sense, so I'm going to label this x, label this y. If that's true, then this side is x. Meaning if I want to establish an equation here where I could maybe compare these variables somehow to an actual value, the value I could compare to would be the 90 meters up here, right? So we're only using these pieces. I'd take 2x, since there's two of those, plus 1y, set that equal to 90. So there's an equation I can use. Now, function-wise, determine the value of x that maximizes the area. All right, we're talking area again. So let's do a of x. Since ultimately we want to determine the value of x, we'll do a of x. That's going to equal, okay, I know we're only using the three sides here, but does that really impact how we're finding the area of the rectangle? No, it's still going to be the base times the height or the length times the width. So it's still going to be x times y. So if I would like everything in terms of x, go back to my equation I've set up, solve for y. Y would be 90 minus 2x. Take that 90 minus 2x, insert for y over here. A of x is going to be x times 90 minus 2x. You distribute your x through, you've got that quadratic you're looking for. Or I'm guessing, based on what you guys want to do on the last problem, using negative b over 2a is more preferable. Negative b over 2a will give us the x-coordinate at the vertex, which in this case will answer our question for that value of x we're looking for. So b, that'd be the coefficient on the x term here, that's 90, negative 90, over 2 times a, that's the coefficient on the x squared term, so that's negative 2. All right, calculating that out, what do we get? We get 45 halves if we reduce, right? Or you could say 22.5, that'd be acceptable. We're trying to determine the value of x, assuming the side associated on the pen with x, or these two sides, our answer would be 45 halves. Now, if we let x be over here, that would change things. So if we wanted to cover our bases, we could also figure out y, right? Another possibility would be 90 minus the 2 times this 45 halves. You know what that is? 90 minus 2 times 45 halves? Come on, you can do that. You got this. It's 45. Good. So the other possibility could be 45. Yeah, this problem's a little open to interpretation because of how you arrange your variables over here.